Any questions up to here? Or I guess any questions, it's always up to here. Unless, of course, you're a time traveler, then. All right. So we're trying to figure out the phase difference between my power supply and either the voltage for the resistance or the voltage for the capacitance. We need to figure out what that angle is supposed to be. When you add phasors, because the voltage across R and the voltage across C should be the voltage across the power supply. When we add phasors, we add them like vectors. Since VR and VC are perpendicular to each other, we create a right triangle here. So sort of drawing that out in an attempt to draw it in the same way. The length of this side is VR, the length of this side is VC, and the length of the hypotenuse is epsilon. So, and there I go, changing it already. I'm just going to write up here that epsilon sub naught equals epsilon sub m, because I'm going to flip back and forth. And again, that epsilon sub 0 is not the permittivity of free space. It is just the maximum value of the voltage coming from the power supply. And I'm trying to find this angle right here, which I'm going to label phi sub 2. Well, I know that epsilon is a right triangle. Pythagorean theorem still holds. Epsilon sub naught squared is equal to VR squared plus VC squared. And as I'm writing this equation, did we do this all part already? Ohm's law applies, because these are all maximum values. So this is, well, it's the same current flowing across all of them. So that's I times R squared. This is I times X sub C, the capacitive reactance squared. And that's going to be equal to the current times something here. Have I talked about that yet?
But does it have to do with one of these formulas over here?
It does. I don't have the symbol over there. The symbol that we use for this, when you're talking about the circuit or coming out of the power supply, we use the letter Z. And Z stands for, pretty sure I did write this down, at least the word, impedance. From at least Anna's expression, I have not written the word impedance down before. I got at least two heads, or at least a head shaking now. An expression and a shake. And the word is pronounced impedance, not impedance. So I have, so one thing, first off, notice I have not written down a formula for impedance. And if you go to the summary section of chapter 22, whatever chapter we're on, let's see, we've done the homework quiz on 22, so this will be chapter 23. Or 32, as I sometimes will say. They will give you a formula in the back of the book, or in the summary section. That is a formula for impedance. It is not the formula for impedance. This is the formula for capacitive reactance. This is the formula for inductive reactance. This is the, well, this is Ohm's law. But the formula for impedance is specific to a setup. So on a quiz or test, if you see that formula, do not automatically apply it. First ask yourself, is this the formula for this situation? Going to factor my I squared out, so what I'm left with is I squared, or I guess square everything. I squared z squared is equal to I squared r squared plus I squared x sub c squared. Obviously, I have a common term here. I can factor it out, divide by it. We end up with z squared is equal to r squared plus x sub c squared. And so for this particular situation here, for the RC series circuit, z is equal to the square root of r squared plus x sub c squared. We'll plug in numbers in a moment. But at some point in the lab, you're doing on Wednesday, you'll use this formula.
Are we gonna have to, derive it each time? Like, are we gonna have to find the formula each time, or are we gonna have like a certain set that we're like, okay, this one fits the best?
A common question that you given on the AC circuit problem is, what's the formula for the impedance?
Okay.
So you usually have to do some sort of manipulation and figure out what it is for that particular circuit.
So just to clarify, doing the derivation to find the formula for that situation is something we will be expected to do.
Yes, that is definitely fair game. All right, so we still haven't found phi yet. That's sort of a side note, because as I realized we hadn't done that yet. All right, so I know that the tangent of phi, sub 2, is equal to VC over VR. Again, it's just a right triangle. It's opposite divided by the adjacent. So phi sub 2 is equal to the arctan of VC over VR. But we don't know what those are yet. But we can narrow it down some. That's going to be equal to the arctan of I times x sub c over I times r, which is the arctan of the capacitive reactance divided by the resistance. In a typical problem, you're given R, you're given C, you're given omega. This is typically the type of thing that you are given in a problem right here. So you would know those values. Yeah, get it back there. And so we can figure out what that phase there is. So let's actually do some numbers. Make it slightly more concrete. Throw another layer in there. Let's say that we have a frequency of power generation of 60 hertz. And we have a resistor of, we'll just say 500 ohms. And a capacitor of make sure I get the right order of magnitude here.
Are you using the capital C and the capital X sub C interchangeably here?
No. Capital C is the capacitance that we all know and love and have for months. X sub C is specifically capacitive reactance, which involves the omega. All right, so in the absence of that, let's go off memory then. I might change this number later in the problem if it comes out to be too off. 30 microfarads. We'll see how that plays out. All right. If this were a test problem, one of the questions would be, given this information, what is omega? What is the angular frequency? So how do you find it? Flashback to simple harmonic motion, the relationship between frequency and angular frequency is the same.
Is this one of those like lambda equals something with these lambda involved? I remember that there were like 3 variables. Could have been a 1 over, lambda equals 1 over the frequency.
I'm sure we could work that in there. Not the thing that pops into my head right off the top. All right, first off, what is frequency?
Is it the number of cycles of the sine or cosine wave in the period?
Okay, per some unit time. All right, so frequency is how often something happens. If I'm now talking about an angle, so if we think about going back to, I have a wheel here spinning about the center. I have some peg sitting right there, sticking out, and the whole thing is rotating around at some angular speed, omega. And I look at the shadow, so I have a light above. I look at the shadow that's being cast down here. So frequency deals with the number of times it oscillates back and forth within, usually per second. Angular frequency deals with basically the number of times it goes around per unit time.
So it's not the angle, it's the number of rotations it makes in a unit of time.
Sorry. If you did number of times it goes around per unit time, that would be in something like revolutions per second.
Right.
Typically, it's in radians per second. So how many radians in a revolution?
2 pi.
And so 2 pi is the factor that separates the two. So if it goes back and forth 5 times a second, this thing goes around 5 times a second. So the angle it would go through would be 2 pi times that. In other words, omega is 2 pi times the frequency. That's a good equation to know. So angular frequency is 2 pi times 60, or 360 pi. Or, if I do that properly, 120 times pi, which is
376.9. Well, almost 377 because it's 0.99.
units,
Yeah.
radians per.
Second.
Yep. So now I have a value for omega. Let's figure out what x sub c is. X sub c, it's a set formula. It's 1 over omega times c, and this is where I find out if my order of magnitude is right over there. So it's 1 over 377 times 30 times 10 to the negative 6. And while you're figuring that out,
Did you guys get 88.4?
Yes,
so what you get?
88.4.
The dreaded question.
Oh.
Oh, the units, well, this is capacitive reactance, right? Yeah.
It is?
It'll probably have two inverse units, right, because omega is radians per second,
Okay.
so the inverse of that would be seconds over radians, so the unit's probably seconds over radians times the units of capacitance, which I can't remember.
Farad?
Farad.
Seconds per radian farad,
Oh,
otherwise known as
a pain in the butt.
an ohm.
Oh.
We have,
That was good.
looking at the relationship here, we have voltage is equal to current times something. Each of these has voltage equals current times something, so these all have to have the same units. I'm gonna change my resistance over there, just so it's not too dramatic. I'm just put a little decimal point right there, it's 50.0. I want the capacitive reactance and the resistance to be same ballpark. All right, so, well, I know the capacitive reactance, I know the resistance now. We can now figure out what that angle, phase angle is. So this is the arctangent of 88.4 over 50.
Where's that 500? Oh, it's 50.
I changed it.
Okay.
So to clarify, these, oh, wait, never mind. Okay.
That is arctan, right?
It is.
I got 1.056.
I got 60.5.
That's because you're in degree mode.
Oh, I actually don't know how to change that. I'm gonna have to learn how to do that. Thank you.
That's what I got at first, and then I was like, wait, I think I'm in degree mode.
Yeah. Being in radians is helpful here. Because in the lab, you'll be given that phase shift in radians. Anyone else?
I get the same thing.
Okay. So, I need to erase stuff. Because the board is never gonna be big enough. Actually, while we're here, before I start erasing, let's go ahead and figure out what the impedance is. So that's gonna be 50 squared, square root of 50 squared plus 88.4 squared.
How do we know to use that formula? Is it just because we have both of those values? Because you said it changes per situation. Well, no.
Right, it comes from basically when I'm figuring out my maximum voltage here, epsilon sub naught, I'm adding VR and VC.
Oh, so it's like Pythagorean.
Yeah, and so it comes out of that.
Okay.
Pythagorean theorem pops up a lot.
If they weren't perpendicular though, we wouldn't use that formula.
Right, then it gets far more complicated.
Okay. So we're just gonna hope that it's perpendicular, like every time.
Yeah,
Okay, good to know.
now, truthfully, when I'm writing a 152 test and I do the AC circuit problem, I don't intend for it to be really complicated. However, I have messed up on 252 tests and made it far more complicated than I intended it to be. And that shows up in their master set. I figured they got more time. Anyway, what do we got?
$101.6.
Yes. Same.
Units?
This is the impedance. Wait,
It should be ohms
ohms
because
squared?
both of them are ohms.
You do the square root, so,
Can you take a moment just to explain the subscript on the epsilon? Unless you said it earlier before I walked.
All right, so.
Okay, then don't worry about it, I'll watch the lecture. Don't worry about it.
Where did you go? No, I am gonna go into it just slightly here. Epsilon sub 0 is what I've been using for years. And I've been moving along fat, dumb, and happy, and then in a 252 lecture afterwards, the student came up and said, why are you bringing permittivity into it? Because that's the same symbol we use for permittivity of free space, except in theory, the permittivity is a lowercase epsilon, and that's an uppercase epsilon. At that point, it hit me that, oh, I am using the same symbol, and perhaps didn't make it clear, so I tried to switch over to E sub m, epsilon sub m, for a maximum value, but habit keeps sending me back over here. So that's why I wrote that up there.
Nice.
There was one other piece of information I do need to give you. So, but let's write down what we do know. So impedance for this problem is 101.6 ohms. Capacitive reactance is 88.4 ohms. Resistance, well, it's still part of the problem over there. And we have that phi sub 2 is equal to 1.056. And so now let's get some space. Any questions before I continue erasing?
I just don't know what phi sub 2 is, but again, if you've gone over it already, I'll just watch the material.
Phi sub 2 is just the angle between these two phasors.
Why the subscript?
Because I'm using, I have phi right there.
Which indicates just one part of that angle? Like just the part above?
All right, so we have phasors that are zipping around. So again, picture, I've got an arrow or dial, a spinner that's zipping around. At time is equal to 0, when we start the problem, the phasors have to be somewhere. It's not like they come into existence after we started the problem. They exist, we start the problem. This right here is telling where the phasor for the power supply is for